Welcome to the Aerospace Advantage podcast. I'm your host, John Slick Baum. Here on the Aerospace Advantage podcast, we speak with leaders in the DoD, industry, and other subject matter experts to explore the intersection of strategy, operational concepts, technology, and policy when it comes to air and space power. So if you like learning about aerospace power, you are in the right place. To our regular listeners, welcome back. And if it's your first time here, thank you so much for taking the time to join us. And as a reminder, if you like what you're hearing today, do us a favor and follow our show. Please give us a like and leave us a comment so that we can keep charting the trajectories that matter to you most. This week, we are going to dig into a key technology that you've seen in the headlines a lot these days, Hypersonic Strike. So let me start with some basics up front to make sure we're all on the same page. Hypersonic is defined as going 5 times the speed of sound. Now, to put that into context, that means you could go from New York to LA in about 30 minutes. We are talking exceedingly fast. The propulsion technology, airframe materials, and thermal management involved with that sort of flight is incredibly demanding. You're talking about extreme heat, pressure, and physical factors that extend well past anything we normally deal with these days. Now, the reason you've heard a lot about hypersonics lately is we're in a race with our adversaries, especially China and Russia, in developing operational capabilities, and we are not at the head of the pack. It's got a lot of people really worried because if you think developing hypersonic technologies is tough, imagine defending against them. The irony is that for decades, the US was the leader in hypersonics thanks to its work with aircraft like the X-15. It flew at hypersonic speeds dozens of times between 1960 and 1968. Since then, we've pursued a few test programs, but it really hasn't been a priority for defense leaders. That's all changed now that we find ourselves falling behind our adversaries. It has caused a massive reset in the Department of Defense, with numerous surge efforts launched to help America regain its hypersonic edge. Things haven't gone entirely to plan, with some notable test failures, but we've also had some successes. Bottom line, this is a race we have to win, so it's going to take a concerted effort by DoD, the science and technology community, plus industry to close the gap. So that's what we're going to talk about today. We're going to learn more about this technology and get a better sense of why we don't want to be second best, and talk to 2 individuals who are key figures in this journey, Dr. Mark Lewis and Dr. Dick Hallion. They are both longtime friends of the Mitchell Institute and 2 of our nation's top hypersonic experts. Dr. Lewis has served in several key jobs, including Chief Scientist of the United States Air Force and most recently as the Director of Defense Research and Engineering for Modernization at the Department of Defense. He now leads the Emerging Technologies Institute at the National Defense Industrial Association. Dr. Hallion is a longtime expert regarding everything aerospace power. He began his career as a founding curator at the Smithsonian's National Air and Space Museum and subsequently served in a number of jobs throughout the United States Air Force, including at the Flight Test Center at Edwards, and in the Secretary of the Air Force's staff group, and as the Air Force historian. Gentlemen, I can't thank you enough for being here.
Thank you for having me.
My pleasure. Delighted to be here.
Okay, gentlemen, let's start out with the problem statement. Why should we care that other countries like China and Russia are probably ahead of us when it comes to hypersonic technologies? We've clearly flown systems like this, and we've clearly flown that fast before. We backed off, and we've been okay so far.
I would say, first of all, we're not developing hypersonic systems, or we shouldn't be developing hypersonic systems just because Russia and China are doing so. We should be developing them regardless. Russia and China, though, are setting the timetables. They're becoming the pacing threat. So that's driving this sense of urgency in delivering these capabilities. In my mind, look, hypersonics is really all about survivability. It's about developing systems that can react quickly, that can confuse an adversary, that can use maneuverability to their advantage to make them harder to stop, not impossible to stop, but harder to stop, and truly reflect the next step, I believe, in our weapons capability. And that's why we need to be pursuing this technology.
Following on what Mark said, hypersonics is a natural evolution in weapons technology. You know, if you take a look at hypersonics and the threats we face today, particularly the growing threat rings of air defense systems that are pushing us away from coastlines and pushing our aircraft away from the targets they need to hit at a time when some of our airborne weapons are relatively short range. Hypersonics gives you that ideal combination of speed and innate reach. You're reaching out automatically at least at a mile a second, maybe 2 or 3 miles a second. And it services a whole set of targets, a whole variety of military missions. And above all, what it enables you to do is it enables you to take information that you have that in the old days would have been considered fleeting intelligence that you could not act upon, and you can turn that fleeting intelligence into actionable intelligence.
Okay, well, now I absolutely get it, and it is a serious game changer. Dick, you are the historical expert here, so how did this happen, and where were the leaders in the 1960s, and why are we coming up short now?
I think it's because we've been always big project driven. And so if you took a look at the 1950s, we made some remarkable advances in hypersonics, both in missile technology, but particularly in the technology of reentry systems. And that served us very well, of course, as we entered the ballistic missile era. And of course, we applied that to the human spaceflight program as well. But looking at winged hypersonics, we always saw that in terms of aircraft would operate in what we now term the transatmosphere, encapsulated by systems like the X-15, or maybe orbital global ranging systems like the abortive X-20 Dinosaur or the aerospace plane concept. But these were big ticket items, and people fail to realize, I think, that this research, development, test, and evaluation base that we were producing on the basis of very vigorous hypersonic research that was really quite remarkable, even by the standards of today, that base was really generating 3, not 2, broad streams of future development. The 2 that we always recognized were global access systems of one sort or another, or space launch systems. But the 3rd stream that I think our adversaries picked up more than we did was on the hypersonic missile. The hypersonic missile used for theater ranging or perhaps global ranging offensive action. And that's the threat that we see posed now by China and Russia.
So as always, I agree with Dick, absolutely 100%. I think that there were a number of reasons why we frankly fell behind. First was a certain degree of hubris. We thought we were so far ahead, no one was going to be able to catch up with us. We could take our sweet time. The second was the hypersonic research community itself having a habit of, frankly, overselling, pushing concepts. We'd have one small accomplishment. The next thing you know, we're trying to build a single stage to orbit vehicle that can take off from any runway and land again after completing some miraculous mission. And so there was a little bit of overselling, a little bit of hype. But there's a third element. And very frankly, there were some very poor decisions that were made. And this was made by leadership within the department. So, for example, the Air Force accomplishes this incredible milestone in flying the X-51. It was a program operated by the Air Force Research Lab. 4 flights. The first flight was mostly successful. The 4th flight in 2013 was almost 100% successful. And in fact, the most exciting thing about the flight was that the data was actually kind of boring because it was everything we expected. The vehicle performed exactly as we predicted, both on ground tests and simulation. So what did we do? Did we build on that? Did we capitalize on it? Did we build more? Did we fly more? No. The Air Force actually stopped the program. And even worse, handed over much of its funding to another agency, handed it over to DARPA. And, DARPA is not constructed, constitutionally, they're not an organization that wants to pick up someone else's work. They're an organization that's always looking to push the boundary. And so the result was you almost had us starting over from scratch in the realm of air-breathing propulsion. That big investment that we made in the X-51 program really didn't come to nearly as much as it should have if we had capitalized on that accomplishment.
I'm going to add to what Mark said and expand it a little further and take a look across agencies. NASA had a very vigorous role that was centered largely on space, but it was birthed out of an organization, the old National Advisory Committee for Aeronautics, that had a solid, substantial record in transonic, supersonic, and hypersonic aerodynamic and propulsion and structures research. NASA applied much of that to the space side of the house and saw hypersonics only in terms of lifting systems such as the space shuttle or planetary exploratory systems that would have to enter the atmosphere of other planets, things like this. There was a wane of interest in looking at systems that might operate in the transatmosphere, even though NASA engineers, particularly out of the Langley Research Center, were producing thousands and thousands of reports and technical notes that have been of incredible value to our potential foes in terms of catching up. We have essentially given the world a roadmap on what works in hypersonics, what approaches to take, and more importantly, what approaches to reject. And then taking a look at what happened within the service community, I completely agree with what Mark just said. The services had multiple problems with hypersonics. I think one was they had so many basic needs, fighting wars that arose in the Balkans and contingencies and Operation Northern Watch and Southern Watch and post 9/11, and then the big strategic thinking community saying the nature of warfare has changed. We no longer need these systems that are redolent of Cold War thinking. Now everything is going to be low intensity conflict, special operations. That all pulled and tugged and hurt developing cohesive, integrated joint planning to look at a hypersonic future. Beyond that, within the service, we made a mistake. And a mistake that was made, I think, within the Air Force was repeating a problem that the old Army Air Corps had in the 1930s. In the 1930s, we were on the cusp of an aeronautical revolution. And that cusp was the turbojet revolution, which began in late 1939 with the flight of the world's first turbojet-powered airplane. But we relied on outside scientific organizations, the Bureau of Standards, the National Advisory Committee for Aeronautics, to guide our investment. And so the Air Corps of the time missed the significance of the gas turbine and didn't learn of it until 1941, when we were exposed to British engine technology. And that was why the United States was third in the gas turbine race, just like we're third today in hypersonics, if you think, behind China and Russia. And that's what happens when you entrust too much of your research and development thinking in the hands of people that do not have the responsibility for organizing, training, and equipping military forces. That's the function of the chief of staff of the service. And that was missed, I think, sadly, certainly over the 2000s time period. We're catching up with that now. But the offloading of programs in hypersonics from the Air Force Research Lab, which, by the way, has done brilliant work in the hypersonics field, the offloading of that to DARPA was, I think, a terrible mistake. It resulted in a hiccup, a pause, a delay, and worse, it started people thinking, well, what exactly is hypersonics? Is it one big thing? We had these fights that made no sense. Should we go boost glide? Should we go powered? Pick a system, pick just one system and we'll move ahead on that. Hypersonics is like saying classical music. It covers many different things. It's like supersonics. When we think of supersonics, we don't just think of one application. We think of multiple. And it's the same with hypersonics. And I think now we're coming back to that, but we're coming back to that late.
Yeah. If I can point out in 2014, then Chief of Staff Mark Welsh released a brilliant document. It was looking at the future of air combat. It included a section on technology, of which hypersonics was the first technology that General Welch's document listed, which was phenomenal. The Air Force communicated to the entire world the importance of hypersonics, and then really failed to capitalize on it. So if you're sitting in Beijing, you get this document from the United States Air Force that says, hey, look at that. Hypersonics is really important. Let's go invest. And we failed to capitalize. We failed to invest on our own. And that's why we find ourselves playing catch-up.
China's interest in this field was evident in international conferences and papers that they were doing as far back as the late 1990s. There was a study that National Defense University undertook in the 2010 time period. I was on it, where we were taking a look at cross-straits relationships between China and Taiwan. And China at that time already had very robust plans for its missile forces, and hypersonics figured prominently even at that time in that. And Mark, of course, has tracked the almost exponential rise in the number of technical papers presented by Chinese engineers, engineering students, and professionals at international conferences in the field of hypersonics. And more significant than that, the extremely rapid rise in sophisticated, redundant, interlinked, and internetted research, development, test, and evaluation establishments, coupled with a tremendous effort to grow a young, very far-seeing, very aggressive cadre of hypersonic researchers. Now, I think we're turning the corner in that, largely because of work that Mark and people like Mike Griffin and Mike White and Gillian Busey have been doing in the more recent era. But for a very long time, when you took a look at hypersonics in the United States, we had a decline in facilities, a drop in programs, a lack of leadership focus on the issue, and the hypersonic experts were retiring or dying off.
Dick and Mark, I appreciate the historic rundown because it is so important. I mean, initially studying and looking at hypersonics from the American viewpoint, it seemed like we were on again, off again, but you bring up tremendous points that not only were we turning the programs on and off, we just had too many cooks in the kitchen and then handing it off midway through, and it just seems like we got completely disorganized. But I do want to bring it back for our audience quickly because you did mention boost, glide, and air breathing. Just getting back to the basics quickly, if we can just have a quick differentiation between the two. And Mark, if you want to get started with that, would be great.
Sure. So as you point out, two basic approaches to building a hypersonic system. One is the boost glide, where essentially you use a rocket to accelerate a glider up to hypersonic speed. Rocket separates from the glider, glides to a target, completes its mission. On the air breathing side, we call it air breathing because that means that the hypersonic vehicle is using an engine which has an inlet that swallows air as it flies and uses the oxygen in the air to burn with fuel. Sometimes they're traded off against each other. They should not. Each of those technologies has its own pros and its cons. Whenever I hear Dick mentioned there have been instances where we've made down select between those two technologies. That's absolutely wrong. They're complementary. One doesn't replace the other. The way I like to think about it is the boost glide systems invest all the energy up front. So you overspeed, you get up to really high speed, and then you bleed off energy as you fly. The air breathers release the energy throughout the flight. So it's a different energy profile. The boost gliders can go a little bit further. They tend to be more maneuverable because you're not worrying about the performance of an engine. But because you invest all the energy up front, they're going to higher Mach numbers. That means there's more stress on the thermal protection system. The air breathers lend themselves to cruise missile type configurations and cruise aircraft. They tend to operate at a more steady Mach number across the board. It means the thermal protection requirements are less severe. So the materials limits are less severe. There are compromises in maneuverability, but the beauty of the air breathing system is they package really well. They can be much more compact than the rocket's powered system. So, for example, if you look at a rocket boost glide that might come up, that would be air launched compared to an air breathing cruise missile. Generally, for summer performance, the air breathing cruise missile is smaller, it's therefore more compact. I can get more on board the aircraft. As a typical number for some of the concepts we're looking at, you can get tens of air breathers, say, in the bomb bay of a B-52. Whereas the boost gliders are too large to fit in the bomb bay, so you got to put them under the wing. So you're limited to maybe 2, maybe 4. So again, you really need both. I think it fits in terms of the high-low mix that we saw in the fighter, in the F-15, F-16. There's a high-low mix of hypersonic systems as well.
Now, following on what Mark said, the example I always point to is Mark's favorite system, which, by the way, he played the lead role in pushing. We would never have had it not been for Mark, and that's the X-51. The X-51 was a milestone hypersonic research vehicle, the most significant hypersonic research vehicle developed since the time of the X-15. And it was no coincidence that it was the 51, because Mark picked that deliberately to echo back to the days of the X-15. But the thing about the X-51 was that if you look at it, it was sized to basically match the GBU-28. This didn't happen deliberately, but when we think of hypersonic missiles, people think, how can you possibly apply those to aircraft? They're going to be big, complex. We can't really do this. The size of the X-51 is completely consistent with a strike aircraft. It's exactly the same, basically, in dimensions and weight as a GBU-28 that we of course introduced at the very end of the first Gulf War. So you have here something that can be carried by an F-15E Strike Eagle aircraft or its equivalent. And that's the kind of thinking we need to look at. These are practical systems. Hypersonics, I think people imagine that this is still something in the future, still something untested. We have had over 100 years of thought in the hypersonic field, almost 100 years of hardcore engineering and research in the hypersonic field, and almost 70 years of where we've actually flown hypersonic vehicles. When you take a look at this, that's really quite remarkable.
Yeah, absolutely. And, like we've mentioned, historically, it seems like we've done a lot of work, but we just have failed to really produce something that America needs. One thing that we often say at Mitchell is obviously the enemy has a vote here. So how have you seen our adversaries approach the technological challenge in recent years? I mean, we don't need to go into classified conversations or anything, but I understand that they seem to be doing pretty well in the field of hypersonics.
Yeah. So first, it is a tribute to the capability of our own intelligence services that they have done such a phenomenal job of informing us what our peer competitors are doing. I'm actually going to now say I now say peer adversaries as we can witness by what's going on in Ukraine today. The Russians, and to a larger extent, I think the Chinese, by any standard, are now ahead of us. And they've got there by building on our work. They basically took our homework. They read our reports, they read our papers. In some cases, they exfiltrated information. They used all the classic means of getting information, infiltrating. And they have made a whole of government investment. I mean, the Chinese treat hypersonics as a source of national pride. They view it with the same significance that they do the development of nuclear weapons and their space program. They invest at universities, they invest in building major national facilities, including wind tunnel complexes, and they brag about it. I mean, we don't actually have to wonder, because they were nice enough to show off their array of hypersonic weapons in 2019 at a military parade. They did YouTube videos showing off their hypersonic test facilities, and then they publish the data coming out of those facilities, and they show us what good facilities they are. They're really paying attention to physics. So my hat's off to the Chinese, because frankly, they have learned how to do things that we used to do, and now in some ways do them better than we do.
I think a point that Mark made that really needs to be stressed is that the revelation that China and Russia were working hypersonics as hard as they were at achieving IOCs on their weapon systems should not have come as a surprise. It was not a surprise to the intelligence community. I was dismayed when we started seeing articles over the last several months saying that this was a Sputnik moment and how had we failed to perceive what was going on. We didn't. The intelligence community did very fine work in warning people. That was why we had studies such as the why and whither studies as far back as 2000, why we had a study on defense, a very influential study that Mark and I were on defense against high-speed weapons in 2016. There's been a whole range here. The problem has not been intelligence failure. It's been leadership failure to act upon intelligence warning. And that is really most unfortunate. I think the underlying rationale between Chinese and Russian work in hypersonics has been a very simple one, basically. They have looked at us, where we are based, how we need to operate from those bases, and they have seen hypersonics quite rightly as the logical means of cutting our sea and air and land lines of communication. You can really do some very interesting things with timely hypersonics going against lines of communication. And of course, on top of that comes strikes on command and control and bases and things like this. But at the same time that they've been working very much in this direction, I think we've seen, unfortunately, from our perspective, I think Mark's perspective and mine, we've seen a leadership slowdown. We've seen this characteristic thing that has always plagued hypersonics, paralysis by analysis. Let's have one more study. Let's do a series of studies. Let's do war games. Let's do simulations. Let's contact some outside organizations to study this. And meantime, our adversaries are moving very rapidly in this field. They have given us the roadmap that we need to follow.
Well, Dick, you mentioned that we have experts in this field, in this technology, that have either retired or you said died off. And I think about infrastructure that we probably don't have that we need. But in your analysis, do we have a shot at catching up? And what do we need to do? And how would you advise the leadership? Because you mentioned it being a leadership failure, frankly.
Well, to put it very bluntly, we need to, and this is actually something we've needed to do over the last several years. We need to move very rapidly toward weaponization of hypersonics. We have already demonstrated that we have the understanding, the technical understanding to address both the challenges of boost glide and the challenges of air-breathing hypersonics. We just need to get on and do it. I was dismayed at some of the statements coming out of the leadership at the most recent Air Force Association meeting, where you had individuals talking about possibly pausing, not quite certain what hypersonics brings to the fight. The idea that, we have problems with our fifth generation fighters getting in close to targets because the air defense systems are so powerful now that if we get in close to try to release short range weapons, the fifth generation system itself is endangered. And then in the same breath, practically saying, but we don't really see why we need to push ahead with hypersonics as rapidly as we do. And it's what I mentioned at the very beginning of this podcast. And that is that what hypersonics gives you is that it gives you that innate reach. It gives you that ability to use legacy systems, fourth generation, early fifth gen, later fifth gen, whatever it is you're looking at, to hold the enemy hostage at a distance. But you don't get that by constantly searching for what's next, what's better, and not developing what you have at hand. We need to just get on and do this.
Right. And I've got to ask Mark, and I really appreciate that response, Dick. But so, Mark, as the former chief scientist of the Air Force, what if we meet our goals? How do you see us, as Dick said, we need to, weaponize hypersonics. So how do you see this impacting operational concepts and the associated technological investments?
So let me start by saying, echoing some of Dick's comments. So one of the great advantages of hypersonics is it allows you to use a tactical system and produce strategic results. Think about the effect of a hypersonic missile against an aircraft carrier. That's a $25 billion asset with however many thousands of lives on board. Think about an adversary that can create a runway so we can't even get our Air Force in the air. That is a significant strategic effect that can be produced by this class of weapon. So I think it's absolutely critical, not that we simply counter this, but that we have our own capability and we deploy it. And that gets to the point, it isn't enough to simply do demonstrations. We can't do onesies, twosies. We can't fill a missile tube here, a missile tube there, and declare ourselves done. We need to be deploying hypersonics at scale. That means hundreds, eventually thousands of weapons. The question that we need to be asking ourselves is, what will give a potential adversary pause? 2 missiles sitting in a tube, 4 missiles on a truck. That's not going to make anyone hesitate. But 1,000 missiles, a bomb load of 20 hypersonic cruise missiles at a time coming out of a B-52, hypersonic weapons coming off the wings of F-15's fifth generation fighters. That would give any potential adversary pause, and that's when we need to be moving through.
Yeah, no, and I appreciate that. And going off of something that Dick said earlier, what about the needs of the industrial base to get to that scale? Is there anything that we used to have that we need to gain back, or just things that we need to build from scratch?
There are several things. So one, we have allowed our test infrastructure to atrophy. We were decommissioning wind tunnels at about the same rate that the Chinese were building new wind tunnels. As just one example, the engine of choice that we think would power a hypersonic cruise missile is something called a scramjet engine, a supersonic combustion ramjet. Today, if in the United States you wish to test a full-scale scramjet engine, you got 2 choices. You can go to the NASA Langley 8-foot facility, or you can go to the Air Force's Arnold Engineering Development Center AP2 wind tunnel. They are both fully booked. So much so that I had a colleague tell me recently that they were set to do a test at AP2 in Tullahoma, and there was a delay in producing the model due to COVID, and they were looking at a potential months-long delay in being able to get back into the tunnel. That is not a sustainable model. So we need to be investing in ground test infrastructure, 1. 2, we need to recapture our ability to do flight tests. Actually, recent years, we have essentially failed in almost every one of our flight tests. Why is that? Well, I'll offer several reasons. One, we've forgotten how to do it. But if you're not repeatedly doing something, you don't retain your competency. We have gone to a model where we test onesies, twosies every couple of months, every couple of years. We can't sustain a flight test rhythm. We cannot maintain our competence if we take such a leisurely path. Then there's another thing we need to worry about, and that is the workforce. And Dick brilliantly alluded to that. In the 1980s, we spun up a workforce for the National Aerospace plane. And those folks I was a graduate student at the time. The folks who were professionals are already retiring. We need to invest in workforce. Now, I will say there's good news on the horizon. The Department of Defense, especially the Joint Hypersonic Transition Office, has invested in this marvelous university consortium. It's a $20 million a year effort. It's got more than 90 universities working on DoD-specific problems, headquartered at Texas A&M. It's kind of a new experiment of how to work with universities, and it's going spectacularly well. Similarly, you've got organizations that are stepping up to the plate in both ground testing and flight testing. Private companies that are investing in capabilities and want to present those to the government. Say, look, we've heard your call. We've made the investments. Now come use our system. And I'd say, so it's really now up to the government really to provide the demand signal. Say, okay, we appreciate those investments. Those were necessary, and we need to go forward and capitalize them. And then finally, you're exactly right. Industrial base is really important. If you're going to build thousands of hypersonic weapons, that's a very different proposition than producing, a single demonstration vehicle. So just as one example, if you're doing boost gliding systems, you need high temperature materials for the thermal protection system. Well, the industrial base delivers, a set of thermal protection materials once every couple of months is very different than the industrial base that can produce tens or hundreds of such weapons a month. And that's what we need to be looking at.
I'd like to add on Mark's comments very quickly in two regards. First of all, he talked about the 8-foot high temperature tunnel at Langley. As Mark well remembers, we had very, very difficult times convincing NASA to actually keep funding that tunnel. There was a long stretch of time where NASA hypersonic partisans who wanted to keep that tunnel and recognized its value were fighting their own agency, which wanted to put that money into space exploration and other things. The point Mark makes on flight testing resonates with me. I always considered myself a flight test guy, and I think he's correct, very, very much correct. I think that we have lost to a great degree that casual familiarity that we had with flight test professional execution that you had all the way through the 50s and 60s, 70s, and into the 80s. We've gotten away from that. I think in part it's because we've become too enamored of things like computational fluid dynamics, simulation, flight simulation. I was thinking of this when I read the Wall Street Journal this week, where there was an article by Kate Batchelor Odell on the critical challenges that fighter pilots are having now across the services in maintaining currency because of the decline in flying hours. And it prompted some very interesting letters to the editor, and the fighter pilot community obviously recognizes this is a serious problem and that we need to increase the number of hours. But there are at the same time people saying, well, we can do all this really with simulation. Do they really need to do that much flying? And of course, anybody who's actually flown realizes that there is a world of difference between a simulator and a real aircraft. Well, it's the same thing here, where you can have all kinds of analysis, but in the last moment, basically flight tests comes down to something being launched in free flight. And while it's fine if you have a flight test to have acceptable risk so that you lose something on the frontier of flight, you don't want to lose it on the way to the frontier. And too often we've had test articles fail because of inadequate pre-launch preparation, failure to follow checklists, other things. You don't want those kinds of moments, particularly in a time period where a test program may only consist of 3 or 4 or 5 or 6 vehicles to begin with. That's no way to run the business. Worse, it causes people to presume that there is something innately wrong with hypersonics or innately not of value. It's a little bit like the problems we had in the early 80s in the days of low observables, early flight testing of low observable systems. We had several accidents that were totally unrelated to low observables. And nevertheless, we had the Government Accountability Office, GAO in the day, basically questioning the whole function and purpose, and the Union of Concerned Scientists and things like this saying, gee, if you're having these accidents, then maybe this isn't really the way to go. It's conflating many different things. We need to just move ahead smartly, but professionally. We need to accept risk. We need to turn testing faster, and we need to be rigorous in test preparation and test execution.
Yeah, and Dick, I could not agree more. And one thing that I will say, I had the opportunity or have had the opportunity to observe a lot of the flight tests that's going on. And I'll call it flight tests because it's what it is with SpaceX at Starbase in Boca Chica. And speaking with the engineers, they're already designing iterations that they know their previous example is obsolete, but they are learning as they're building, and they're accepting a bit of risk and a bit of failure so that they can just keep that learning curve at least at a 45-degree angle and continue to ramp it up. So I couldn't agree more. And it really has that, to your point of flight test, it really has that right stuff feel, if you will, for those that are familiar with the movie. But I do want to transition a little bit, and I'll steal a quote from the right stuff. No bucks, no Buck Rogers, right? So we know that hypersonics are not going to be cheap. And as I understand it, we're going to have to make some choices, and tough choices. So I just wonder, as you see we ramp this up, how do we leverage, what we do know works well, and how we could ramp up, for example, maybe going after air launch systems first that may not require such a big booster compared to like a ground launch system. So what are your thoughts on how we could increase capability and capacity at the same time?
My thoughts on that, all we have to do is take a look at what is happening in the Ukraine. The Ukraine has been a salutary wake-up moment for the West. We have gotten away from this idea of force-on-force major clashes with peer competitors who have very robust kinetic military forces. And this has shown why you need to be able to reach out, hit forces like that very rapidly, very hard, very decisively, with precision weapons that can reach over hundreds, maybe even thousands of miles and achieve effects very, very quickly. And if you're going to do that, really the best way to do that is by having an air launch system where you have an aircraft that is carrying a weapon. It may be a boost glide system. It may be a scramjet, hypersonic cruise missile approach. But we need to reorient our thinking. Particularly, I think we need to reorient our thinking from this obsessive concern we've had with low intensity conflict, soft power, the counterinsurgency type way of thinking. We need to recognize that this is much more like the balanced force structure that we were required to have at the height of the Cold War. We need to be able to defend our forward forces. We need those forward forces to be robust and able to project power over a great distance. And that right now argues very powerfully for hypersonic missiles coming off various things. They may be off aircraft, they may be off unmanned aerial systems, they may be off ships, surface launchers, whatever it is. But this is the weapon choice today that we need to invest in, much like we invested in the precision laser-guided Baum and JDAM of actually several generations ago.
So if I can dive in, I like to make the observation that the most expensive weapon is the one that leads to your loss. If you lose, that weapon was the most expensive weapon. It's not the cost of the unit, it's the cost of the effect. And that includes opportunity costs. So if, for example, I am shooting missiles that fly at Mach 0.7 against an adversary that's shooting missiles that are flying at Mach 5 or Mach 6, think about the other losses that I incur. The loss of aircraft, the loss of surface ships, while I'm waiting for my weapons to hit his target as they're responding to me. I think too often we do a poor accounting job. We think about the cost of the individual missile, not the cost of the effect. If my weapon is twice as expensive, but 5 times more effective, 5 times more likely to penetrate the target, well, then I've certainly won. But let me also dispel another point. It is almost taken as a given that hypersonic weapons are not affordable. Well, let me start out by pointing out somehow the Chinese and the Russians seem to have figured out how to afford them because they're building them and they're deploying them. Let me also take issue with this notion that just because it's fast, it has to be expensive. For example, a hypersonic cruise missile, a scramjet-powered cruise missile, has very few moving parts. The cost is in the manufacturing. It's difficult to manufacture, for example, cooling passives in the engines, but there are few moving points. So intrinsically, there isn't that much that should make it that much more expensive than a low-speed system. We just accept this as a given. And I think that's wrong-headed, and that's led to some very poor decisions.
And following on what Mark just said, as early as 2005 and 2007, Mark and I were giving briefings on this and the value of hypersonics. And we pointed out the fact that you're really developing systems here that are, in effect, time warfare. It's the elaboration of John Boyd's OODA loop. You're getting inside the enemy's OODA loop simply by the speed with which you're able to hit him. And so Mark's point about here we are with 0.7 cruise missiles and somebody else has something that's 5 point or above, well, that's a point that's very well taken, because there are options there that we are ceding to the opponent that we should possess ourselves.
Yeah, I couldn't agree more. I mean, this is just, we're just inside of the intercept timeline, and whoever can get there faster, right? We are getting a little bit long on time, so I'm going to wrap it up with one last question for each of you. So how do we know that we are getting it right with hypersonics, and what does winning look like? So Dick, let's get started with you.
The way you determine whether you're winning is when you have IOC on the first air-launched hypersonic system, when you can actually deploy a hypersonic weapon and that system is operated by ACC, and for that matter, for our sister services when they have IOC in their systems, because that will indicate you have the numbers right, you have the systems right, and you're at the point where you're actually introducing something into an operational construct. Now, that's just the first step. You know, we had IOC on the F-117 stealth fighter in 1983, but we really didn't have a capability there that was very strong until the 1989 time period into 1990, coincidentally with the Gulf crisis breaking out in August 1990. Once you get to IOC, that doesn't mean the problems are over, but winning is when you get to the point that you have more than a few. You have enough that you can have training, test and evaluation rounds, follow-on testing, and you have munitions bays loaded with weapons, and the systems are on alert.
So Dick has once again captured exactly my thoughts. I would leave with this, though. In my mind, winning means we've gotten to the point where we're no longer asking the question, why do we need hypersonics? And instead we're asking the question, well, why wouldn't we want this? And that, to me, is the intellectual leap that we need to make. It's not something that, it's not a nice to have. It's not a G. It's a boutique system. The simple reality is, every time we did war games in certain major scenarios, the side that didn't have hypersonic weapons was the side that lost. Period. End of discussion. If we are facing peer competitors who have large numbers of hypersonic weapons, and we do not have those, we will not prevail. It's as simple as that. So that's why this is so incredibly important.
Yeah, I couldn't agree more, Mark. And gentlemen, I just want to say thank you so much for joining us today. You both bring such incredible experience and perspective to us at Mitchell, so thank you so much for being here.
Thanks very much. It's been a pleasure.
Thanks so much for having us.
With that, I'd like to extend a big thank you to our guests for joining in today's discussion. I'd also like to extend a big thank you to our listeners for your continued support and for tuning in to today's show. If you like what you've heard today, don't forget to hit that like button and follow or subscribe to the Aerospace Advantage. You can also leave a comment to let us know what you think about our show or areas you think we should explore further. As always, you can join in on the conversation by following the Mitchell Institute on Twitter, Instagram, Facebook, or LinkedIn, and you can always find us at mitchellaerospacepower.org. Thanks again for joining us, and we'll see you next time. Stay safe and check 6.